Hello, welcome back. The title of this lesson is called Geometric Sequences. This is part one of several lessons. So the geometric sequence is something that you learn usually somewhere in algebra, but it's kind of there and we use it for some concepts there in algebra, but really it doesn't come into its own as something really useful to know about really until a little bit later in math, in pre-calculus and calculus. So when you study this for the first time, you might wonder, why do we care so much about it? But the reality is that we just need to learn it now so that we can have it in our tool bag for later math classes, in which case it becomes extremely useful. Now, the good news is geometric sequence is very simple to understand. If you remember back to the arithmetic sequence, those were sequences of numbers where basically we're just adding or subtracting a constant number to get each of the terms. Like we might add 3 to get the next term, then add 3, then add 3, then add 3. Okay, so add or subtract numbers to get those arithmetic sequences. For a geometric sequence, basically what we're going to do is we're going to start with term number 1 and we're going to start multiplying. Instead of adding or subtracting, we're going to multiply by a number, multiply by a number, multiply by a number. So the term geometric sequence just means a sequence of numbers where you end up multiplying to get each subsequent term. Now what I'm going to do first is write down the formula for all of the terms of a geometric sequence. You probably won't understand exactly why it's the way that it is in the beginning, but by the end of this lesson you will understand exactly why that equation for the geometric sequence works, and we're going to solve several problems in the concept of geometric sequence. So here is the formula for geometric sequence. Okay, here it is. Not too complicated. The nth term down the road is equal to the first term in the sequence, t sub 1, multiplied by r, I'll explain what that is in a second, raised to the power of n minus 1. So this is an equation that you will definitely see in all algebra books at some point, pre-calculus, calculus, and so on. And as I said, it becomes extremely important, especially in calculus 2, not even in calculus 1, but in calculus 2, it becomes extremely important to understand what the geometric sequence is. So the question that we have is, okay, I can tell you that this is the equation of a geometric sequence, but why is the nth term equal to all of these things? So in order to do that, we have to write a few things down. None of them are very hard to understand. All right, so the first thing is, I already told you the terms of a geometric sequence are basically when you multiply by a number to continue getting the terms in the sequence. Another way of saying that, the way that you're going to see it in your textbook, is that the terms of the geometric sequence, they differ by what we call a common ratio. So what I actually like to tell you is the terms of the sequence have a common multiplier, right? But you don't see that written in books. You see it written as a common ratio. I personally find it easier to understand thinking about it as a common multiplier, but I'm going to show you both ways to think about it. Both of them are extremely easy to understand. So what I need to write down first is that the geometric terms are related by a common ratio. In almost all books that I've ever seen, this common ratio is just called r. In fact, that's why I have r in the equation. So this r is what we call the common ratio between the terms. But what I like to tell people is that it's all related to what we call a common multiplier. I don't know why, but for me, it's just easier to think of things being multiplied to get the future terms rather than some division, which is what a ratio is. A ratio is division. All right, so let's understand this by taking a look at a very simple geometric series. So this guy is a geometric series. 5, then we have 10, then we have 20, and then we have 40, and then some ... down the road, we have t number 10, okay? So we have term 1, term 2, term 3, term 4, a bunch of terms in the middle, and then here's the 10th term way down at the end. First of all, how do you know that this is a geometric series and not an arithmetic? Sorry about that. Sometimes I say series because we're going to be talking about geometric series and such very soon, which are also very, very important. So in this lesson, if I say series, please forgive me and just understand that I'm trying to tell you about sequences here. So anyway, how do we know this listing of numbers is a geometric sequence rather than an arithmetic sequence? Well, you just look at the terms. Here I've added 5 to get 10, but here to go from here to here I've added 10, but to go from here I've added 20. So all of the common differences between the terms, they're all different. So this is not an arithmetic sequence. So how do we know it's a geometric? Geometric sequence? Well, to go from here to here, what do I do? Well, I'm going to multiply by 2. 5 times 2 is 10. How do I go from here? 10 times 2 is 20. How do I go from here to here? 20 times 2, whoops, not times 20, times 2 is 40, and so it goes. To get the next term after this, I would multiply by 2. To get the next term after that, I'd multiply by 2. And I keep multiplying and multiplying and multiplying. Eventually, I get to term number 10. Or if I want to take it out farther, I go to term number 100, term number 5,000. You can just keep multiplying by 2, by 2, by 2. In this case, this, what I call the common multiplier, is a 2, right? So in this case, we say common multiplier is equal to 2 for this particular sequence. Now let's rewrite the sequence, and let's talk about it more like what you would see in your textbook. This is the way I like to think about it, but let's write the same sequence down. 5, 10, 20, 40, dot, 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 and the 10th term somewhere down the road. All right? What do we mean when we say geometric terms are related by a common ratio, which is also called a common multiplier? What is a ratio? A ratio is just a division. A ratio of 1 to 2 means 1 divided by 2 means a half. A ratio of 2 to 4 means 2 divided by 4, which we can simplify to 1/2. So when you divide two numbers, it just means you're taking the ratio. So if you take and look at these first two terms, and you take the second term divided by the first term, 10 over 5, of course you get 2. So what this means is the ratio between these terms is 2. The ratio between the first two terms is equal to 2. R is equal to 2. Now if you examine the second two terms, the ratio here is 20 over 10. I'm taking a look only at these two terms, and so the ratio again is 2. Same ratio. This ratio right here is again 40 over 20. So the ratio is 2, and you can see that going down the line, the ratio between all of these terms are going to be 2. So it's exactly the same thing. What we say is that we say the common ratio is equal to 2. And it's the same common ratio, all right? And because of that, what we basically mean is that to get the next term, you can think of it as all of the adjacent terms have the same ratio. That when you predict the next term in the future, you need to pick that term so that when you divide it by the previous term, you still get 2. That's what basically you do. But to me, that just turns my brain in noodles, okay? I don't think of things that way. So for me, it's much easier to take this common ratio and think of it as a common multiplier. Keep multiplying, 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 multiplying. Whatever you get for your common ratio, it's the same thing as a common multiplier. That's how you get your future terms. Now, I want to rewrite the sequence one more time over here because I'm going to draw a very important conclusion. 5, 10, 20, 40, dot, 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 and then we have the 10th one down here, okay? And we already said that the common ratio here was 2. The common ratio here was 2. The common ratio here was 2. Presumably there's some common ratio here, and then there's some common ratio here. All of them are equal to 2 between all of these adjacent terms in there, okay? Now the question I have for you is, how many ratios do we actually have here? Well, if you have 10 terms, right, that's what I have, 10 terms here, then I think you can convince yourself that there's 9 ratios. And there's a total of 10 terms. So do you see how when you take a look and see how many ratios you have, there's always one less ratio than there is number of terms. There's 10 terms, of course, all the way to number 10. But because I'm looking in pairs like this is 1 ratio, 2, 3, 4, 5, and if you go all the way out to the 10th term, there's always going to be one less ratio because you're looking at pairs of terms. So in this case, there's 9 ratio, but 10 terms. So how would I decide or calculate ahead of time what would term number 10 be if I want to calculate what this is? Well, if I want to figure out what it is, I just start with the first term and multiply by 2. That gives me the second term, right? So I could say 5 times 2. That's going to give me that second term. But then to get the next term, I just have to multiply by 2 again. See, 5 times 2 is 10, times 2 is 20. But then I multiply by 2 again and I get the 40. You see what's happening? Here's 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here's 5 times 2 is 10, then 20, then 40, then 80, and go da 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 all the way down here. You should have 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications by 2. Because there are 9 ratios, there are 9 multiplications by 2 to get over here. So there are 9 of these. So what does all this mean? If I want to calculate what the 10th term actually is, it's going to be, we'll do an equal sign. It'll be 5 times 2 to the power of 9, because an exponent means you're multiplying by itself with a total of 9 of them there. So 2 to the 9th, 5 times 2 to the 9th power. Now, if you were to run this through a calculator, the 10th term actually turns out to be 2,560. That's what it comes out to be. When you keep multiplying by 2 over and over again, this is what you get by the 10th term. But I want to turn your attention back to this. This is the secret sauce right here. Notice that the 10th term down in the future was just equal to whatever the first term was, multiplied by this common ratio, but raised to the power of however many terms I had minus 1, because that's how many multiplications I actually had. So we can generalize this, and we can say that the nth term down the road, whatever number term we want to go to, not the 10th term, but just whatever random term we want, we just start by the first term, 5, and we start multiplying by 2's. How many times do we multiply by 2? We just do it n minus 1 times, because that's how many ratios we're going to have, is the term we're trying to get to minus 1, right? And this is 5, of course. So let me replace 5 with t sub 1. We'll make it general, okay? So we'll say that the nth term of any geometric sequence is just equal to the first term of the sequence times, and instead of 2, let's replace that, and we'll say that that is going to be whatever the common ratio for that sequence is. All right? So t1 times r to the n minus 1 power, t1 times r to the n minus 1's power, this is exactly what the geometric sequence is. This is why the geometric sequence is equal to, this is why the equation is what it is. It's because to arrive at whatever term you want down the road for any sequence, you just start with the first one and start multiplying by this common multiplier, which is in all books called the common ratio. And how many times do you do the multiplication? Just n minus 1 time. Whatever term you're trying to get to, minus 1. This is why the geometric sequence equation works the way that it works. So now we have enough information to start solving some problems. And you're going to find out that even though a lot of students will say, well, why do I care about this? Geometric sequence, who cares? But the reality of it is, it's kind of nice, because none of these problems are going to be hard. If you're doing 10 pages of work for these problems, you're working too hard, okay? None of them should require that much work. So what I want to do for these sequences is find an equation for the nth term. If you are asked to find the nth term, they want you to generalize it to give that equation. So what if you have 2, 6, 18, 54, ... You could have, t sub n sitting out here. And I want to give an equation for t sub n so that I could put in the value of n for whatever term I want and just immediately calculate what the answer is going to be given the geometric sequence equation. So the first step is to figure out what the common ratio is. So what you do is you take a look at these terms, and you say that the common ratio is this term divided by this one. So the common ratio is 3. And you do the same thing. 18 divided by 6 is 3. You do the same thing here. 54 divided by 18 is again 3. The ratio is the same in all cases, so this is a geometric sequence. If one of these ratios was different than 3, like if the first two a ratio had a 2, but the third one had a ratio of 1 or 4 or 6 or whatever, then it's not a geometric sequence. For it to be a geometric sequence, every pair of terms in the entire sequence has to have this common multiplier, or you can think of it as the common ratio. All right, so we need to write down this equation for the nth term. The nth term is always equal to the first term times whatever the common ratio to the power of n minus 1. All right, but in this case, the first term is 2. The common ratio is 3 to the power of n minus 1. Okay, so you just write down t sub n, 2 times 3n minus 1. Now you have to be really careful here to make sure you understand that this n minus 1 exponent only applies to the 3. You're getting that as a number, and then you're multiplying the result times 2. So this is going to give you whatever term you want in the sequence. Let's go ahead and just spend a second to check it for a couple of terms. Let's go over here. Let's see what happens if we put t sub 1 into this equation. Find the first term, right? So we're saying that it's 2 times 3 to the n minus 1. N minus 1 being n is equal to 1 minus 1. We're just putting the value of 1 into this equation. Well, you're going to get 2 times 3 to the 0. So t sub 1, this is 1 times 2 is 2, and that's the first term of the sequence. We'll do one more. 2 times 3 to the 2 minus 1. All I did was put the number 2 into this equation. What are you going to get? 2 times 3 to the 1 power, which you know is 6. That is the second term. You could go and put n is equal to 3, n is equal to 4, and recover all these terms. And then you could go beyond 4, putting 5, 6, 7, 1,000, 1 million in there, or whatever, and you would get whatever that term is of the sequence. So you don't have to, even though I introduce all of this as starting at the first term and then times 2 and times 2 and times 2 and times, and that's how you can get the terms, of course. But if you want to calculate the 1,594th term, you're going to be multiplying a long time. You don't want to do that. What you want to do in those cases, figure out what the equation is and just put the term number in here, calculate it, and that's what you're going to get the answer. All right, next problem. What if I have 3, negative 12, 48, negative 192, ... Do not worry if the terms alternate in signs like this. We're going to see how that works out. All right, so what do we get right here? This common ratio here is going to be this divided by this, negative 12 over 3. So what do you get? Negative 4. Now all of these should have exactly the same common ratio, otherwise this is not a geometric sequence at all. So this ratio is 48 over negative 12, and you can see this is going to then be negative 4. This common ratio, negative 192 over 48, if you grab a calculator, you're going to find this is also equal to negative 4. So this is a geometric sequence as well. So how do we write down what the equation for the nth term is? It's the first term. I'm sorry, the nth term is equal to the first term times the common ratio to the power of n minus 1. The first term was 3. The common ratio, you need to wrap it in parentheses because it's a negative sign. The common ratio is negative 4. And then you have the n minus 1 right here. So you say the nth term is 3 times negative 4 n minus 1. It's really important when your common ratio happens to be negative. This is the thing that has to go in the base of this exponent here. So you need to wrap it in parentheses so the negative sign is the exponent is also acting on the negative sign as well. Now let's just take a second to check these, or at least check a couple of them. Let's go ahead and take a look at what would happen if we take a look at t sub 1. We're saying it's 3 times negative 4, and the power is n minus 1, so we're going to put 1 minus 1. So this is 0, so what you're going to get here is 0. Negative 4 to the 0 power is 1, times 3 is 3. That's the first term in the sequence. The second term is 3 multiplied by negative 4 to the power of n minus 1. I'm putting n is equal to 2, 2 minus 1. So what you're going to have here is 3 times negative 4, because the exponent is just 1. So then you get negative 12. Negative 12 is the second term of the sequence. So keep on cranking through, and you can recover all of these terms, and then you can go beyond it to get to whatever term you want. Now these are not too bad whenever you have numbers like this that we can easily divide and all, but students sometimes get completely tripped up whenever the sequence has radicals or other weird things. If you see radicals in your sequence, or if you see fractions in your sequence, or if you see, who knows what else you could see, some kind of exponents or fractional exponents in your sequence, the same principles hold. In order for these things to be geometric sequence, you have to divide each of those terms and make sure that they have the same common ratio. And then you use the exact same equation. Nothing changes. So don't try to invent new math if you see a sequence that is weird. A good example of that will be the following. The first time I saw the sequence, I was like, whoa, this is kind of weird. The first one is 1. Then you have square root of 2. Then you have 2. Then you have 2 times the square root of 2. Then ... Now the first time you look at this, you're like, this can't be geometric. It's so weird. Okay, but you cannot look at problems and decide if they're geometric or not. You just can't. So what you have to do is calculate what this common ratio is. So let's go off to the side. Square root of 2, which is the second term, divided by 1. Square root of 2. So this ratio is the square root of 2. Now each of these other ratios better be square root of 2, otherwise this thing is not even a geometric sequence at all. So let's try it. What do we get for the second one? It's 2, this term, divided by square root of 2. First time you look at this, you're like, well, that's not equal. That's not the same thing. But then you remember, well, wait a minute, we don't want radicals in the denominator. Let's try to get it into the same form. So what we can say, 2 over root 2, we can multiply by the conjugate. Remember, multiply by top and bottom by square root of 2 over square root of 2, which is just multiplying by 1. This is just 1, so you haven't changed anything. So on the top, you're going to have, let's do it down here, 2 times the square root of 2 over, when you multiply these, you multiply what's under the radical, so it's square root of 4. So what you get is 2 times the square root of 2 over, this becomes 2. The 2's cancel, and what you get is the square root of 2. So it turns out that even though it doesn't look like it, actually when you simplify it, the common ratio does in fact equal square root of 2. So far we're pretty good. Let's check the third one just to make sure. This guy better have the same ratio. So we're going to check it. 2 times the square root of 2 divided by 2. Obviously these cancel, you get square root of 2. So the common ratio here is again square root of 2. So even though it doesn't look like it in the beginning, it has exactly the same common ratio. So it is a geometric sequence. Okay? And even though you have radicals, you do the same exact equation. The nth term is the first term times r to the n minus 1. All right? So then the first term is 1. The common ratio is the square root of 2. So go ahead and put that in parentheses as well to make sure and not confuse it or kind of get confused with the radical, and the power is n minus 1. So what we're saying is that the nth term is 1 times this, so I can drop that, square root of 2 to the power of n minus 1. This is the final answer. Now, especially when you have a weird one like this with radicals, it's a really good idea to go ahead and try to check your work. So let's go ahead and at least recover the first couple of terms here. First term is going to be square root of 2 to the power of n minus 1. But the term is 1, so it's 1 minus 1, so that's a 0 power. So the first term is 1. That's exactly what we have. Then the second term should be the square root of 2 to the power of n minus 1. But n is 2, so it's going to be 2 minus 1. That's a first power. So T2 is square root of 2. That's exactly the second term. Keep going through it, and you'll find that the third term and the fourth term are easily recovered as well, and then you can predict any term beyond that. Notice that the same exact equation was used for this. Didn't matter because there was radicals or weird things going around. If it's a geometric sequence, then it's just going to use the exact same equation. All right, one more quick one, and we'll be done. The sequence goes as follows. 64, negative 48, 36, negative 27. Now, most people, including me, would not be able to look at this and decide if it's a geometric sequence or not. I mean, it's pretty easy when you're looking back at something like, something like this. Oh yeah, multiply by 2 each time. But I don't know about you, I'm not going to be able to determine what the common multiplier, what the common ratio is just by looking at this. So you must do the divisions in order to convince yourself that it is geometric. So let's take a look and figure out what is the ratio here. Take this term, negative 48, over this term, 64. Okay? What do you get here? Well, I can divide the top by 8 and divide the bottom. I can simplify the fraction, in other words. So divide the top by 8, I'm going to get negative 6. 8 times 6 is 48, so negative 6. And then divide this by 8, I'm going to get 8. But I see that I can simplify this further. I mean, if I were smart, I could pick the right factor, but I didn't initially. I just knew I could divide by 8 and by 8. Then I look at this and say I can divide this by 2. So I can say divide by 2, I'll get negative 3, and divide by 2, I'll get 4. So the ratio is negative 3/4. That's as fully simplified as I can get. Now, when I check the rest of these guys, I had better get negative 3/4 for each of these other common ratios. Otherwise, this thing is not even a geometric sequence at all. So what do I have here? I'm kind of running out of space here, I guess. I'll change the colors, and I'll just go way over here, something like this. So the ratio is going to be 36, this term, divided by the negative 48, right? And I can divide these by 12. 12 times 3 is 36. 12 times 4 is 48. And that's negative 3/4, the same as this. And then I can take, let's change colors again. I can take these guys and find this common ratio as negative 27 over 36, negative 27 over 36. And what do you get there? You can divide by 9. 9 times 3 is 27. And 9 times 3 is 27. So we're dividing by 9, so it's 3. And then 9 times 4 is 36. So negative 3/4, same as the rest of these guys. So same common ratio, same common ratio, same common ratio. It doesn't look like it has the same common ratio. The reason it doesn't really jump out at us as much is because the common ratio, not only is it negative, but the common ratio is a fraction. So what we're doing is we're saying, if you take this and you multiply this by negative 3/4, you're going to get this. If you take this and multiply by negative 3/4, you'll get this. If you take this and multiply by negative 3/4, you'll get that. Now, I'll leave it to you to verify, but that's what it means, okay? So how do we find the nth term? It's just the first term, right? The first term times the common ratio. Now, because it's a fraction and because it's negative, it's always a good idea to wrap it in parentheses. And you have the power of n minus 1. Now, the first term is, what, 64. So it's going to be 64 multiplied by negative 3/4 to the n minus 1. 64 times negative 3/4 to the n minus 1. You must wrap this common ratio in parentheses to make sure the negative, that the exponent applies to the negative as well as the fraction. And if you could just check right away, if you put a n is equal to 1 here, you get a 0. This to the 0 is 1. The first term is 64, which is what you expect. Put that second term in there, and third term and fourth term, you'll be able to recover these just like we have been able to for all of the previous problems. I'll leave that as an exercise for you. So here we have conquered the very first part of geometric sequences. You know, a lot of books just throw this thing at you and say, here it is, guys, it's a geometric sequence. And then a lot of students start getting in the habit of just memorizing it or using it, but they don't have any idea what they're doing. So when you get to a problem that is a little different than the basic problem, then you don't know what to do because you don't really understand anything. So what we did is we went through and talked about, here's a geometric sequence. This is why it's a geometric sequence, because it has a common multiplier, which is also the exact same thing as a common ratio, because multiplication and division are closely related. So common ratio, common multiplier, same kind of thing. That's how you recover the terms. And then we basically said, if you take a common, like 10 terms, for instance, then you have 9 ratios. So to recover that 10th term, it's just the first term times the common ratio 9 times, which ends up recovering what that equation is. So that's really what I want you to pull out of it. The problems are great, but I really want you to understand what the equation means. Solve every one of these problems yourself. Make sure you're getting the correct answer. Follow me on to the next lesson. We're going to work some slightly more challenging problems with geometric sequences.